Hello everyone, so welcome back. This is the fourth lecture of business statistics in R. So last time, I think we already talked about how we are going to visualize a normal distributions and binomial distributions, and using the um, P norm, R norm, Q norm, and D norm functions for normal distributions for different statistics we are trying to calculate. And we also talk about how to use those different binomials, probability functions, right, to get some results in returns. So today we are going to introduce a new distribution, which is called a student's t distributions, and usually short for t distributions. So t distribution is usually what we use to demonstrate the sampling distributions. So the whole idea for sampling distribution is to create a distributions that allow us to evaluate for multiple samples drawing from the populations. And we are basically having a conceptual idea about if we drawing enough samples multiple times, right, or maybe 100 times or several times, to ensure that we are getting the information from the populations, the means value of the samples each time we draw will centralize, right? Will stack up in the middle of the distribution, and that middle point or the means of the sample means should always be a good representations of the population mean value. And the standard deviations from the samples mean also will be a unbiased estimator for the population standard deviations. So today we would like to introduce the t distribution so we can do some hypothesis testing later, right, that we introduce in the next lessons. Well, just like the previous time, let's try to plot the t distribution and see the shape of these t distributions. So we begin with setting the mean value of this distribution equal to 0. And then we will set the standard deviations equals to 1. And we are going to create an x-axis value, which is going to be from -4 to 4. And we are going to have 10,000 intervals within this range, -4 to 4. And every value in this sequence will multiply by the standard deviations plus the mean, so that we can actually create a spread of the x-axis here. So let's save that. And for every value that we created here in this sequence, we want to map it to a y value, which is the probability, right? The distribution, the density values. So we are going to basically use the density function, dt. So dt basically means the density for t distributions. For every x value we created, and we are going to have the degree of freedoms in this example set to 29. So we create the y values, and then we plot the x and y. And this time we're going to use a line, right, to demonstrate the distributions. And we have the x label, which is the t statistic score. The y label will be the density of the distributions. And the title will be student t distributions with degree of freedom 29. So let's see how it looks like. So we don't actually have anything plotting out yet because actually we don't have the line function yet, but at the end actually take out all the unnecessary graphs, right? So what we're going to do is to basically draw the line for x and y axis here. So now we see the x and y graphs, and we're going to basically give some lines for this graph. So one, actually it's a vertical lines at 2, and the other one is a -2 vertical lines, and we're going to give an x-axis here. So this basically gives you an idea how the t distributions looks like, and in the later time we can understand how we are going to find the t statistics to figure out the probability, right, in this distributions functions. So again, the idea is, well, I have the locations here, -2, right? So this is basically similar to the normal distribution. We have 2 standard deviations away from the center, and also the positive 2 indicates, right? So we also have like 2 standard deviations away from the center point or the mean of these distributions. The shape of the t distribution should be similar to the actual normal distributions for the populations. But one thing worth to note, if we have a very, very small degree of freedom, so that means we have very small number of observations to plot these distributions, unfortunately, we might only have a distribution that is very widespread because we're not very confident it's going to look like a population's distribution. However, if we get enough sample size, for instance, anything above 30 or maybe close to 50, the distributions of the t distributions should look almost the same, very, very close to the actual normal distributions. So again, well, the concept I have explained in the class, and hope that you can now see the distributions and imagine the shape of it. So in your class activities or practice, there are some questions that you might need to calculate the t value, right? The t statistics. So basically, are the scores on the x-axis, right, of these distributions. For example, if we're given a population mean in our study, which is 23.2, and we pick some sample, and the sample mean is 21.8, and we know only the sample standard deviation, which is 5.8, but I have no idea about the population standard deviations, then what I'm going to do is to use this sample standard deviations as my reference point, right, to kind of like give an idea to calculate the unbiased standard error of the sample means, which is the estimated population standard deviations in this case. But of course, to calculate the estimated standard deviations for the populations or standard error of the sample mean, we need one more piece of information, which is the sample size. So to calculate that, the t statistic is not that difficult. So all you need to do is to subtract the sample means by the population means and divide it by the standard error of the sample distribution, which is the t distributions. So to calculate the standard error, you need to use the standard deviation of the sample divided by the square roots of the sample size. So let me try to run this, and the result is negative 1.4482 in this case, or A3. So that means somewhere close to this side of the distributions. So that's the location, that's the t-score of the distributions. Well, given another case, let's say I have the population means 155.7 and the sample mean 160.6. And I want to calculate the standard error with the sample deviations 14.8 and sample size 68. So I plug in basically everything back to my t-statistic equations. I calculate this, and this time I get a positive number, which is 2.73, somewhere closer to the right-hand side of the distributions. You can also try to imagine, we can actually, given the t-statistics points, right, the locations of your t-distributions, and ask the reverse questions. I want to know what is the sample means value that actually give me a t locations, right, a t statistic 2.5. So in this case, we have a target in the distribution, which is t equals 2.5, and we know the population means, and we know the sample standard deviations and the sample size. So we want to actually do the calculations in the reverse. So you can definitely do this in algebra and figure this out, but I'm going to show you right here. So it's basically the t statistics multiplied by the standard error of the t statistics, right, or these sample distributions, and this time plus the population's means. So let's see. So the sample means that is going to give you a 2.5 locations on the t-distributions somewhere here. The mean score, the sample mean score, has to be 58.24. So again, those are the calculations we went through it in the class, and I hope that you are not confused about that. You're just basically hard coding these calculations here. Well, the next thing that I would recommend you to do is to take a look at some of the applications, right, for using a t-statistics. Especially we want to replicate what we did last time. So we want to use a PT function, which is the probability of t-distribution functions, to calculate the probability on the left-hand side of the locations given in the problems. So for instance, I have the following informations about the populations. 23.2 is the mean of the populations. Sample means 21.8, standard deviations 5.8, and sample size 36. And we want to answer, what is the probability that we randomly select a 36 samples with a mean less than or equals to 21.8? Right, so basically we are trying to figure out, well, what is the probability, right, that we can do that. So what we're going to do is to, of course, first figure out the t locations, right, the t statistics, by using the formula that we just presented earlier. So the locations of the distribution will be negative 4482 or 4483, somewhere around this area here. So we want to figure out the probability where we can randomly select some number in this area of the tail, of the left side tail of the distributions. So what we can do is to use the PT functions. Again, the PT function tells you about the probability of the left tails of the distributions, always. So we put in the locations of these PT functions, and one very important difference between the normal distribution calculations and the t-distribution calculation is normal distributions only needs you to define the mean and the standard deviations of the populations, and then they will calculate the probability for you. In the t-distribution, because the distribution shape changes when the degree of freedom change. So in this case, we specifically asking for a sample size of 36. So the 36 will be the total number of observations, and the degree of freedom will always be n minus 1, which is 36 minus 1 in this case. So you define that, and then you calculate. And there you go. The left tails from negative 1.4483 to the left will have a tail probability of 0.0782. So that means 7.82% of a chance you will randomly select a sample of 36 that has a mean value less than or equals to 21. So this is especially important for you guys to learn because, well, in the later chapter assignments, you will do a lot of these calculations. So when we are doing the left tail calculations, of course, we can just use the PT functions. However, what if we are trying to calculate the probability on the right tail? So here's an example. So let's suppose I'm trying to figure out the t-distributions locations by using these informations given in the problems. This time I want to know the probability for selecting a sample with mean value greater or equals to 169.6. So that means on the right hand side of the tail, obviously. So we first calculate the t-statistics, and this time we get an answer returns 2.73. So we want to know any probability on tail portions, which is pretty tiny right here, that is right to the 2.73 t-statistic locations. So in this case, well, what I can do pretty simple because we know the whole distribution add up to 100%, which is 1. I can literally just use 1 minus the probability on the left hand side, right? And then we will get the leftover, which is the right hand tail. So let's try to run that. And now I get an extremely small value, 0.004, which is 0.4%, which match perfectly fine with our assumption here, because the right hand tail, it's very, very, very small and tiny here. You can also calculate something in betweens, right? So for example, you want to actually calculate the probability between 150 and 160, right? So you select 68 sample, and you want to know what is the probability to have these 68 samples with a mean value between 150 to 160. So the way how we do it is, first of all, calculate the upper hand of the t-statistics, and then we calculate the lower end of the t-statistics. You can actually assign the upper end of the t-statistics to maybe up variable, and you basically calculate the left hand tail of the lower end t-statistics locations and name it to low. So you want to calculate the area between the 2 points. It's pretty simple. You use the upper probability, right, the upper locations probability, and minus the lower location probability, and you will get something just in between. So in this case, the probability in between is 0.9891 or 0.9892 actually. So that means is 98.92%. So again, well, try to think about the relationship between the PT functions and how you can calculate different area. That is going to help you to answer some questions in your assignments. On the other hand, the QT functions, similar to the Q norm functions or the Q binorm functions. The Q functions always give you a locations, right, in return. So in this case, if you want to ask the locations in the distribution that gives 95% of the probability on the left-hand tails with a degree of freedom of 20, so that means we have 21 sample minus 1, which is 20, and we have the lower tail parameter set it to true. So let's see what it returns. See, with the 95% on the left-hand side of the distributions, so that means, well, I want to know the left-hand side will have 95% total, and I want to find the locations where everything add up to the left-hand side will give you a 95%, or the 95 percentiles of the data. And that will give you a locations 1.72447. So somewhere around here. Well, if you want to find the 99 percentiles in the data, well, with a different degree of freedoms, which is 100 this time, well, you can also simply do that, and you can figure out the location will be 2.364. Let's suppose you're trying to find the 95% confident intervals of the t distributions with degree of 45 in our study. So what you can do, it's basically calculate the 97.5% of one tail and 97.5% on the right tail, right, on the other tails. When you combine the two, it will give you a 2.5 on the left hand tail and 2.5 on the right hand tails, right? So again, I'm trying to find the locations here. So I want to know on the left hand side that will contain 97.5% of the probability. So that means I'm trying to find this location on the right hand side of the distributions. So let's run this. I'll get 2.014. So that means somewhere close to this blue line right here. That will give you a locations where the left hand side, the whole thing will be 97.5. So that means the leftover on this right hand tail will be 2.5%. And to the left, we can actually use the parameter here, lower.tail, set it equals to false. And what it means is I want to figure out the 97.5% of the probability, not on the left hand side, but instead this time it's on the right hand side. So the leftover on the left hand side will be 2.5%. So what is this score? And obviously you already know, negative 2.014. And again, why do you know the answer? Because the t-distribution is always symmetric. What you get a score on the left hand side should always equals to the right hand side score to give you the same proportions or probability in the distributions. So QT function is important because you can do the reverse work very quickly. Now, the RT functions and the DT functions are usually used for plotting the t-distributions. So it's not very often that you will use these functions in our course objective. So I'm just going to very quickly demonstrate once when you're going to use RT function and DT functions. For RT functions, it's basically used to generate some simulated data. So we can actually ask R to generate 1000 data points that follow a t-distributions with degree of freedoms of 40. And we call this a narrow data set. So let's run this. And I'm going to generate another simulated data, another 1000 data points. And this time, it follows the t-distribution with degree of freedom of 5. And I call this a Y data set. So I save it. Now I'm going to plot the two graphs. So this PAR function actually allow me to separate the dimensions of a plot, right? It's just like a drawing paper. I split it into two. And this time I want to have 1 row and 2 columns of plots to show. So what two graphs I want to show? Well, first I want to show the narrow graphs on the left hand side with degree of freedom 40, and the next one I want to show the the wider distributions with degree of freedom 5. So let's see. So can you see the results here? So how the random data is so narrowly centralized in the mean of 0 when the degree of freedom is high, and when the degree of freedom is very low, then you will expect to see a very wide spread of the data sets. So in this case, the random sample generated has a much wider standard deviations or spread of the distributions. Well, another interesting function, the DT function, basically used to calculate the density at a given point. So again, for any continuous study that we do in this class, it's almost never a case that we are going to calculate a single point density values, right? So we never say, oh, what is the chance to specifically select sample mean from 36 random observations that has a mean value only equals to 40. Most of the time in the study of continuous variable, we actually make an interval study. So we don't actually do point density evaluations. So for instance, I want to find out, well, the middle points of the distributions that follow a degree of freedoms of 20. What is the probability, right, the density for that one particular point in our distributions? So we run this and it returns. So of course, this is the highest score, highest density you can get. So 39.39, 39.4 almost percent is basically the center point distribution value, right? Probability you can think about if you want. But again, well, overall, I don't think you are going to have a lot of chances to use the RT function and the DT function, so just take it as reference for now. Well, for the rest, I would say, well, try to focus on how to use the PT and QT function to answer the problems in your assignments. So if you have any questions, feel free to contact me, and I am hoping this video actually give you some helps on understanding how to use these t-distribution functions or t-distribution probability functions in this exercise. I will see you guys next time. Goodbye.